Okay, Biology 107 fans, here is a flipped lecture on Chapter 8. It discusses enzymes and the energy associated with enzymes and reactions, which we have discussed sort of all along, so this is going to be a relatively short flipped lecture. We've talked about energy and the fact that the first law of thermodynamics says that energy is conserved, right? So the first law of thermodynamics, make sure you know that. First law of thermodynamics, which is really, I do believe that is physics. Dynamics. Right, so energy can't be created or destroyed. And all energy is in two different forms. It's either kinetic energy, which is the energy of motion, and that can be, right, we've talked about the water that's flowing in a river, and we've talked about the movement of molecules from one place to another. And so we talk about kinetic energy as energy of movement. The second is potential energy, and we have a couple different ways that we can think of potential energy. The second one they say here is the molecular chemical energy, and that's stored in bonds. Right, and so there's a lot of chemical energy stored in all of the molecules that make up your body. There's another kind of potential energy, which we've talked quite a bit about recently, and that's the energy that's stored in gradients. And that is also considered potential energy. All right. What do these energies have to do with reactions? We've talked about free energy of a reaction, and the free energy of a reaction is the amount of energy available from that to do work. So I like to think about this, if you're sitting on the couch, right, you have some capability of doing work. You could fall off the couch, right, spontaneously. And your falling off the couch, if you were tied to a rope and a pulley, could actually lift something up off of the floor. So you have the potential to do you have the potential to do work by being on the couch. Now, if you're lying on the floor, you really don't have very much potential energy because there's not much you can do from there. Okay? All right, let's go to the next slide. The potential energy that we've been talking about recently is the energy that's stored either in bonds, as if we were talking in a phosphate bond, you have that tenuous hold on the electrons, and it's really that you have a lot more potential energy in those bonds than you do when you have atoms that are really tightly packed together. And so we've already covered this relatively. We'll move on. The molecule that our body uses as a source of chemical energy is ATP. And as it's drawn here, notice they're drawing it with a ribose molecule, and I think, right, I said to you that most of the energy that our body has is in this ribose form. It has the 3 phosphate groups that are connected through phosphoanhydride bonds, and right, it has an adenine group, the base. So it's the base, the sugar, and the phosphates, and that makes up a nucleotide. So nucleotides have multiple functions, and the release of energy from this molecule can occur through hydrolysis. So using water, we can chop off that last phosphate, and that releases a lot of energy. A lot of high potential energy is stored in that bond. And when that energy is released, it can then be used to catalyze a reaction. And we talk about how does ATP drive reactions. It has to do with this concept of energetic coupling. We couple one reaction which is favorable. So it's favorable to go from ATP to ADP plus PI. That's a spontaneous reaction. Why is that spontaneous? It's a negative delta G. It's spontaneous because you're going from higher order to lower order. Higher order? What am I trying to say? We're going to more disorder. Yes? So delta S is positive. So most of those reactions are going to generate a negative delta G. And we couple that reaction, the spontaneous reaction, the one that's favorable, with an unfavorable reaction, one that is a positive delta G, right? And in general is usually going to have a negative delta S. Together, those two combined reactions allow for the unfavorable reaction to occur. So this is unfavorable, and this one up here is favorable. What does that look like in reality? Okay, so let's make this a little bigger. And when we look at this, what we're looking at are two reactions. Here's reaction 1. This is the favorable reaction. And this is using energy, using the energy of ATP to drive the second reaction, which is unfavorable. So the favorable reaction, the hydrolysis of ATP, allows us to drive the reaction of A plus B now by making it more favorable. The release of ATP, if we move across, what you see is that the delta G of the overall reaction is what? So if we just were taking A plus B, maybe I should shrink this so that you can see both of these and draw each one individually. So what they're doing here is they're showing you A plus B is here. These are the reactants. And you have the reaction occur, and then the difference between the reactants and the products, like that, is this distance right here. So that is a positive delta G. That is unfavorable. But the other reaction, it's not very unfavorable, it's just slightly unfavorable. The first reaction, the hydrolysis of ATP, right, to ADP plus PI, is highly favorable. And so you have a delta G that is negative, and its value is greater than the value of the positive delta G, right? And so that putting these two together, you end up with a negative delta G for the reaction. Actually, I don't even know if we say that it has a negative delta G. Let's just say that the ATP, the energy from ATP, is used to drive this unfavorable reaction. So the products of this reaction, shown here, are above the delta G for the A and B together, but below the reactants for the first part of this reaction, the hydrolysis of ATP. Okay, so the input of energy can drive unfavorable reactions. So we talk a lot about enzymes. Enzymes act as catalysts. They usually work on one reaction at a time, and you're going to see that almost all of biology is driven by these catalyzed reactions. And you know that an enzyme lowers the activation energy, right? You're going to be able to say this in your sleep, lowers the activation energy. Of a reaction, and it does it by, right, so these are sort of two separate things, by binding the reactants, or the substrates, reactants, and changing their conformation, and basically putting them in a conformation that's more favorable for the reaction to occur. So they bind the reactants, and it's very precise, okay? They do it in that lock and key mechanism. And very importantly, okay, I'm going to say that again, very importantly is you understand that they stabilize some transition state between the substrates and the products. So you have substrates that are going to go to some intermediate state en route to their final product. And that intermediate state gets stabilized by the enzyme changing the conformation of those reactants. That lowers the activation energy. Here's that one example that I talked to you about. If you have substrates, you have substrate A and substrate B. Notice substrate B is ATP. Okay, A and B can fit together into a binding pocket. Okay, so there's usually a binding pocket of an enzyme, and the place where catalysis occurs is called the catalytic site. And inside here, what you actually have are atoms touching one another and stabilizing them in a position that is favorable for catalyzing whatever reaction is occurring. So here we are. Is this a spontaneous or non-spontaneous? Okay, so you look at delta G. That's how you determine this. And delta G is going down, right? So if delta G is going down, that means it's a negative delta G, which is spontaneous. And that's because the reactants here are at a higher free energy state than the products. Here is the transition state shown up here where I have the blue bracket. So the interaction between A, B, and C, those molecules, has a transition state. And that transition state actually requires the input of energy because these guys don't want to be together. Right? Either they're being repulsed by hydrophobic force, van der Waals forces, steric hindrance, whatever that is. They don't want to be together. We're jamming them together. Right? And that's the activation energy required. This is the activation energy to do anything at home when you're sitting on the couch. It's hard to get yourself up off the couch. Once you get yourself up off the couch, it's not so hard to go do whatever that is you needed to do. But sitting on the couch, you have some inertia. And to overcome that inertia, you have to have some energy. Ultimately, that energy that's input is going to be regained because of the spontaneousness of this reaction. Oh boy, I think those are the exact same words we've said before. It lowers the activation energy required for the reaction to proceed, and it does that by stabilizing the transition state of the reactants. Stabilizing the transition state of the reactants. So here you see, in the presence of an enzyme, you're lowering the activation energy significantly, right? So this isn't needed anymore. So this is like incentive. Okay, somebody comes to you and says, I'll give you $100 to get off the couch and go out to the mailbox and pick up the mail. Well, that's a lot of incentive. Okay, you'll be off that couch faster than you can imagine. So the enzyme is allowing for this to occur. It's greasing the wheels, so to speak. It's starting this in motion, and it does it with less activation energy than what was required before. The delta G has not changed in these reactions. It stays the same. You still have the same negative delta G because the reactants are above the products. The delta G doesn't change in the presence of a catalyst. There's some things about catalysts, enzymes, that you need to know. So one of the things is that enzymes are saturable. What does saturable means? Means, okay, well, you can have a certain amount of enzyme in a reaction, but somewhere, right, you're going to have very few reactants, and the enzyme is going to work really fast because it doesn't have much to do. But at some point, if you have too many reactants, right, only so much enzyme can only go so fast. And so I'm going to show you a graph of what that looks like. And it's dependent upon how much substrates are around, how much enzyme is around, and the speed of how fast that enzyme can catalyze the reaction. And so what we call this is that enzymes have kinetics, so they work at a particular speed. In this case, we're talking about speed. Remember I told you, almost all enzymes increase the speed of a reaction. Well, I think that I was actually wrong. I think all enzymes increase the speed of reaction. Some of them don't increase it very much. They increase it from not going to going. All right. But at some point, you can only go so fast because you can only do so much catalysis at a time. So here's this chart that shows you can do reactions without, so uncatalyzed reactions. So here you have no enzyme. And when you don't have an enzyme, it appears that no matter how much substrate you continue to add, you add substrate, you're still going, the reaction is increasing, but it never can actually reach this level because it's actually a very slow reaction that's going not very fast. And so the more substrate you add, the more products you'll make. In the presence of an enzyme, so the red one, this curve shows that there are kinetics of this that you start out and at very low concentrations of substrate, you increase the speed very rapidly. So you are able to catalyze reactions really quickly, but that starts to level off. At some point you reach saturation. And that means that you have too much substrate. You can only, especially when you're out here where it's completely level, you can only go so fast. They're going as fast as they can, right? I can only go as fast as I can. I can't do it faster. No matter how much more work you pile on me, I can only go so fast. So there are a couple things that affect enzyme function. One of them, well, two of them, right, are temperature and pH. Temperature, I think, is pretty obvious. What do you think happens at higher temperatures? In general, most enzymes work faster at higher temperatures. That may not be true for some weirdo enzymes, but in general, you're increasing the speed of the molecular structure of the atoms, and it just allows for things to go faster. Now, pH can affect how fast an enzyme goes because it changes the shape and structure of that particular enzyme. I think I have another. And I think this is going to be the end. So enzymes can have what we call temperature as well as pH optima. Optima. That's where it works optimally, at its best. And so in this image, what you can see on the left, we're looking at temperatures. And right at really high temperatures, what happens to proteins? They get denatured. So there's some place where you're going to be good, you're increasing temperature, and up here, this is a good temperature. But at too high a temperature, you're actually breaking down the proteins themselves. And too cold, right? You're just, think about, you're frozen. Things get slow when they're cold. Similarly, with pH, okay, if you look at the right panel, with pH, some enzymes have, like here, this enzyme here has a optima around pH 7. The red one has an optimal around pH 3, and above and below that, right, you see they both drop off pretty quickly. So optima is very important for maintaining reactions going at their fastest rate. Obviously, if you're too cold, or if you have too low or too high a pH or too hot, those reactions are not going to go as fast as if you're at the optimal temperature and the optimal pH. Okay, I think that should cover it. We covered most of this in class, so I will see you next week. Have a good weekend.